forces. Now we're talking about fields. And there's an awful lot of, hey guys, there's an awful lot of writing already here for us. And in some ways, this feels a little bit like we're reading a textbook together. But I want to make sure that we're illustrating and processing it, okay? So yes, absolutely, we could read a textbook, but what's a field? Well, it's a property of space. Now, another thing that people throw onto that idea is that there's a gradient. Now, this gradient of an electric field, oh, by the way, the variable we use for electric field is this letter here. It looks like a really fancy letter E, but it's actually the Greek letter epsilon. Okay, so there you go, learn something new. But this epsilon, this fancy E, is an E field. And when I say gradient, it makes me think about a slope on a hill. You know, like if somebody's going to grade their backyard for drainage purposes or something like that, or there's a ditch and there has to be a steep gradient on either side of it, there's like a hill quality to a gradient. So when I talk about a gradient of an electric field, what people are typically trying to get at is that it has an orientation. And when people talk about fields, fields have gradients, fields have orientations. A gravitational field, of course, has an orientation oriented towards the center of mass of the system. An electric field, maybe the orientation is a little bit more complicated because here I've got a picture of a positive charge, and the comment says that electric fields orient away from positive charges. I guess implicitly, what does that mean about electric fields and negative charges? Yeah, that seems reasonable. Electric fields orient towards electric charges. So this idea of a gradient, fields slope, if you like, towards a negative charge and away from a positive charge. Now, slope isn't the right word. That's why we use the word gradient, because a slope is something we think of as being a hill or a valley when you're discussing a two-dimensional space, right? A slopiness in a two-dimensional space. A gradient conjures up the idea of slopiness, but of course, a point charge could be in three space. So imagine a slope towards something, but in three dimensions. And when you realize that that's what the gravitational field is around our spherical planet, you're like, oh, okay, yeah, it's a slopiness, a orienting towards in three space, right? Now with gravity, we don't have an orienting away from. We only have an orienting towards gradient. But that's because we only deal with one type of matter. We don't deal with negative matter, if you like, right? Now, if we did have negative matter, and this is something that people have played around with, negative matter would have an opposite field orientation. So anyway, here we've got fields away from positive charges, and maybe I'll just tack on here, and toward negative charges. And if we were going to do a negative charge, we'd talk about, a negative charge. We talk about an electric field orienting toward that negative charge. The next bullet that I have here is the field affects the space around the objects. Now, we know that gravity affects the space around an object, and that if you put a mass in a gravitational field, it will be affected. But what we really have here is similar to gravity, but it's a different fundamental force. It's an action at a distance. Now, the word action at a distance shows up in lots of places, whether it's textbooks or curriculums. But the idea of action at a distance is when you can exert a force on something without touching. So gravity is a good example of that, but electric field force is another example of that. The next jot that we have is that field intensity is simply the intensity of a field. Well, that sounds like a stupid thing to say. That's like saying having money is just the act of having money. Like, that's dumb. But okay, so fields have intensity, and that's what field intensity is a measure of. Great. And it's a description that we're going to deal with as a mathematical model that looks like this. The intensity of a field, so here's my epsilon. It's got an orientation to it, so I'll put a vector hat over top of it. It affects the stuff around it, which means that it exerts a force whenever a charge is present in it. So if there's a charge in the presence of an electric field, there's a certain amount of force per amount of charge. And we kind of have that idea again from gravitational fields. Remember, gravitational fields was newtons per kilogram. electric fields.
I have to go to a training.
Yeah, do it.
But I didn't remember this today.
All right. With electric fields, we talk about units of newtons per coulomb. So, like a gravitational field is newtons per kilogram, electric field is newtons per coulomb. So, again, similarities. Not the same, but similarities and things that we're familiar with. And it's nice to have familiarity. The fourth jot is where the force is the force due to a charge. Force due to a charge. And the field strength can be determined by feeling the force. Okay, field strength, feeling the force. So when we say we're feeling the force, this is the force we're talking about. When we're talking about the force that we're feeling, we're talking about that force right there. A charge feels a force when it's in the presence of an electric field. Really, this sentence is kind of unpacking this equation, right? We're talking about feeling a force because you're in the presence of an electric field. And what's feeling the force? A charge that was placed in that field. Same with gravity. What would feel a gravitational force? A mass that's placed in a gravitational field. How would you talk about the gravitational field? With a gravitational field intensity. Similar conversation. Different fundamental force. So let's draw a picture. I want to draw a picture of an electric field. I'm going to draw it as parallel lines. This is my electric field, okay? And we can label it as epsilon. Got my color coding there. All the electric field is red. And I want to finish this sentence. It says that it's feeling a force on a test charge in that field. All right, so a test charge would be a charge that finds itself inside of the field. This is our Q value that we were talking about with our equation. So I'll just kind of give myself a little label here. This is Q. And dividing by the test charge's magnitude. Now, a test charge, this concept of a test charge, remember, if that's a charge, wouldn't the charge be creating its own electric field? That makes sense, right? Now, when we talk about objects on Earth that are in the presence of a gravitational field, of course, a banana has its own gravitational field. True? But the Earth has a stronger gravitational field. So when I use a banana as my test mass, I don't expect that the gravitational field due to the banana would disturb the shape of the gravitational field around it. Make sense? And so when I say that I'm going to put a test charge in the presence of an electric field, what is meant by a test charge is something kind of like a banana is disproportionately small compared to the Earth. A test charge is so small that its E field doesn't disrupt the field around it. Or the field that it's in. And that's something that I feel like I've had a few people miss over the years. What is a test charge? It's really small compared to whatever it is that's creating this electric field. Just like a banana is really small compared to the Earth. And so we can think of a banana as a test mass in Earth's gravitational field, and it doesn't affect the Earth's gravitational field very much, or at least negligibly, right? So this is analogous in that way. Again, lots of analogies, not the same thing. They're completely different fundamental forces. And I want to take a look at the electric field that's between these 2 point charges. And I have one on the left and one on the right. If you look carefully, the one on the left has a plus sign beside it. The one on the right has a minus sign beside it. What we said earlier about electric field conventions is that the gradient, the electric field orientation, always orients away from positives. And if you notice, there are all these field arrows that are pointing away from the positive one. And they're pointing toward this negative one if you look carefully, but I'm just adding it in for emphasis in case you can't see the tips of those arrows. And then in between, the electric field of one almost seems like it feeds in to the field of the other. And of course, outside of the confines of this page, don't you imagine that this field also feeds in? like as we go further and further away outside of the snapshot of this picture, right? Now, that would be if I have what the chemistry people call a dipole. We call it a dipole too, but you guys have probably talked about polar molecules already. So if you're talking about polar molecules in chemistry, water is probably the most famous one, right? Water might have, it's not quite like this, but there's a positive end and a negative end to a water molecule. And so you might end up having an electric field around an individual water molecule that looks kind of like this. That's kind of neat. Nice overlaps with chemistry. But if I have not a dipole, but two positive charges that are brought near each other. Of course, we know that positive charges will repel from one another. But what happens with the field construction? Well, the field construction goes like this. We know that electric fields orient away from positives, but if these guys both have electric fields orienting away from them, what happens is their electric fields splay off of each other. And I know asymptote isn't the right word, but I'm grasping for a vocabulary word that we know. But can you guys see that there's like this no man's land in between those two electric fields where it looks like right there. I'll just put maybe I'll put a pink spot there. Right where that pink spot is, can you see that the X components and the Y components would cancel each other out? All the fields would cancel each other out, and there could be a spot right in between those 2 point charges where there's no electric field. Notice that between those guys, there would be a very strong electric field. And so you could actually have two positive charges and zero total electric field in the middle because these things are kind of splaying off of each other. That's something to sort of keep in mind as well. And we'll come back to that mathematically in a little bit. I feel like I was working through these jot notes and then I kind of collided with a subheading change here. The collision says electric field lines. Well, okay, we were just drawing that. It's a way to visualize fields. We all know that when we talk about gravitational field lines and gravitational field orientation, you know that there's not literally like threads going through space where you could just like point to a point in space and say, there's the gravitational field line. It's not a physical thing that actually exists. There's not a physical line through space where the field line is. It's a construct. It's a way to talk about the orientation of space due to this fundamental thing that creates a field, right? But with this convention, we have orienting away from positive towards negative, but we also have this conventional idea that the closer the lines are together, visually, the stronger the field is. So look, see how the spacing is far apart out here? Weak field. See how they're close together here? Strong field. So that's a convention that we use. Closer together field lines means stronger. I mean, even when I go back up to my single point source, see how the field lines are closer together in this region than they are out in this region? That suggests to me that the electric field is dropping off somehow as you get further and further away from the source of the field, which of course makes sense to us, right? But visually, the density of the field lines tells us a visual about the strength of the field. That's not really math so much as it is communication. It's good communication, right? So we've got orientation, we've got density. The other thing is that field lines don't cross. This is one where, conceptually, maybe this isn't something that feels good to you, except when I look at this, can you guys see that none of these guys make X's with each other? None of these guys make X's with each other. And if I want to lean on something that I know about gravity and gradients and slopes and hills, you know that if I walk uphill from my house to, I don't know, I got this special someone. No, I don't. If you had a special someone at the top of the hill that you needed to go and visit, you had to go up the hill. No, let's make it a little bit less romantic. You remember the people in olden times say, I had to walk uphill both ways to school. Look, if you had to walk uphill one way to school, could you possibly walk uphill also the other way? And of course, that's the joke, right? But think about what that would mean. If I had to walk uphill on the way to school here, that would mean that school was also here and home was also here. That would be what it's like to walk uphill both ways to school. That would be a hill that crosses. a gradient, a slope that crosses. It's a physical impossibility. It can't be uphill both ways. And so when we talk about electric fields never crossing, that's why. Because it can't have an orientation both one way and the other way simultaneously. It's an orientation, it's a field. Hills are the same, they can't be uphill both ways. And that's why the old joke is funny. I walked uphill both ways. Trying to say that my life was tough when I was young, I suppose. Anyway, using Coulomb's force due to 2-point charges, along with the definition of field intensity, we can find the electric field near a point charge. And so, again, I want to emphasize what a test charge is. I'm going to call it Q test. And I'll emphasize again, it's so small that it doesn't disturb the surrounding field. So small that it doesn't disturb the surrounding field. Like a banana compared to Earth. Just using banana for scale. What this statement is saying that I could take Coulomb's law, with it, which is FEK equals KQ1. And you know what? Instead of saying Q1, Q2, I'm going to say Q1, Q test, just to make use of this test charge idea. My second charge is going to be the test charge, and Q1 must be the charge that's creating the field. It must be relatively large, divided by r squared. It's the distance between those two charges. And my equation 2, I want to choose to be the equation that we just stated up above as our definition of an electric field, is epsilon equals Fe over Q. But remember, the charge that's feeling the electric field is the test charge, Q test. And if I sub 1 into 2, then we'll end up getting this equation. And you can play around with it yourself, make sure that I'm not lying to you. I get epsilon is equal to K Q1 divided by r squared. If you do the substitution yourself, what you're going to notice is that the Q test cancels out, right? And so what that means is that the electric field can be measured as a function of how strong the charge is and how far away you are from that charge. Now, I'm going to put absolute values around that only because this is the way that we could calculate the electric field strength for either a positive charge or a negative charge. I would calculate how strong the electric field is, and then I would decide if the charge is positive, it orients away from the charge. If the charge is negative, it orients toward the charge. So I'm still using that positive negative to deal with orientation, but I'm going to calculate how big it is first, okay? Anyway, this is the electric field due to a point charge. And when I say a point charge, I keep on using that word. A point charge is a charge where all the charges are concentrated more or less at one point, as opposed to like a balloon where you think of the charges when you rub them on your sweater as being spread out over, let's just pretend it's a sphere. Okay, so a point charge is that point where you can consider all the charges to be focused, to be like located at that one position in space. The reason we're not doing distributed charges is because a distributed charge over a spherical surface area is decidedly more complicated than just deciding to pretend that all the charges at one point in space, you know? And I won't go down that rabbit hole as to why it's more complicated. I'm just going to ask for some trust on this one. Okay, so we're going to pretend that all of our charges are located at points. Yes?
What's the point of a test charge then? Where do you test it?
Well, so as a test charge, later on, we'll talk about what that test charge does in terms of accelerating when it's in the presence of an electric field, because we'll talk about particle accelerators a little bit. For now, it's just a little bit of a tool to let us join these two equations together. Yeah. And as a concept, I explained what it was, right? So it's something that we use to test the strength of a field. Yeah. And just in case somehow this has gotten lost in translation, this r is the distance away from the point charge.